Students, today we are going to start the new topic, that is the kinetic theory of gases. Okay, so this is the new topic of your syllabus. So before going to start the actual concepts, we are going to see some introductory part. So we'll see first the introduction. Okay, so we know the matter exists in three forms. Okay, so which are these three forms? One is solid, second one is liquid, and third one is the gas. Okay, so these are the three forms of matter. Okay, so the gaseous state, simply it is characterized by the simplicity and uniformity. Okay, so especially this gaseous state, it is characterized by the simplicity and uniformity in behavior. Okay, so a gas, we know the gas has not definite shape, no definite shape, as well as not definite volume. Okay, so gas, it is not having any definite kind of shape and it is not having any kind of definite volume. Okay, so it has the low density, the gas has low density. Okay, but it has some slight viscosity. Okay, so these are some points about the gaseous phase. Gases, we know they distribute themselves uniformly throughout the available space. If this is the space available for the gas, then the gas molecules they distribute themselves in the provided space or available space. If this is the available space, then gas molecules spread themselves in this shape. Okay, the volume of all gases is affected by the changing in external condition like temperature, okay, pressure. Then if we change these conditions, then the volume of gas is affected. Especially whatever the volume available, it is affected by the change in temperature and change in pressure. The behavior of gas is governed by certain gaseous laws, like we know the Boyle's law. Okay, then we know the Charles law. Okay, then Graham's law of diffusion. Okay, and the Avogadro's law. Okay, so these four laws, these are about the gases. Okay, so gases, these are governed by all these four laws. Okay, so this is the some introductory part. At the time of enunciation of gases laws, means at the time of discoveries or enunciation of these gases laws, these laws were only empirical generalization based on the experimental observations. There was no theoretical background. So no theoretical background was available at the time of enunciation of gas laws. Okay, so there was no theoretical background to justify these gas laws. In 19th century, in 19th century, the scientist Bernoulli, especially Bernoulli, okay, chronic Clausius, okay, Maxwell and Boltzmann. These scientists, Bernoulli, Chronic, Clausius, Maxwell and Boltzmann, these scientists developed a theory on the basis of various gas laws. Okay. These scientists have developed a theory in the 19th century, and this theory is known as kinetic molecular theory of gases. This is known as kinetic molecular theory of gases, and this theory provided the theoretical background for various gas laws. Okay, so in introduction we have put some idea upon the gaseous phase, gaseous type of matter. So this is some introductory part. Let's move towards, we will see the next some postulates or assumptions of kinetic theory of gases. So we'll see the postulates, or we can say that assumptions of kinetic theory of gases. Okay, so the first assumption is any gas consists of large number of discrete, okay, tiny particles. Tiny means small, tiny, very small, tiny particles called the molecules. Okay, so any gas consists of the large number of discrete, and tiny means very small particles, which are called as the gas molecules. Okay, the molecules are so small, these molecules are, tiny means so small, that their actual volume is negligible. Since these molecules are very small, their actual volume is negligible in comparison with total volume occupied by gas. Okay, so there is total volume of gas occupied, and in comparison with this, the volume of one molecule or molecules, it is very small, so it is negligible. Okay, so this is first assumption or postulate of this theory. So what is the second assumption? The second assumption is the molecules are in a state of constant rapid motion in all possible directions, colliding in random manner. In random manner. That means the molecule of gas can move anywhere throughout the available space in all possible directions, colliding on each other in random manner. Okay, and also with walls of the container. That means molecules, they collide with each other also, and on the walls of the container also. Okay, or containing vessel, gas containing vessel. So this is the second assumption. What is the third assumption? The molecules exerts no appreciable attraction on each other. That means the molecules of gas, they do not attract each other, as well as between the molecules. Okay, as well as between the molecules. Okay, and walls of the vessel in the given in which the gas is contained, and wall of container. What is the meaning of this statement? There is no attraction between the gas molecules and with the walls of the container. That means molecule and wall, there is no attraction between these two. Okay, the fourth assumption is the molecular collisions, okay, on each other are perfectly elastic. Okay, so what is mean by this? There is no net loss of energy. We know when the molecules collide with each other, they transfer some energy, but in case of gaseous molecule, the collisions are perfectly elastic. That is, there is no net loss of energy. Okay, if the molecule collide with one another or with walls of the vessel. Okay, then the fifth assumption is the pressure exerted by gas is due to the bombardment. This is important. Bombardment of the molecules on walls of the container. Okay, that means we know the molecules are in continuous motion. While they are moving from one point or other, they strike the gas vessel where the gas is kept, and due to this collision between the molecules and the wall of the vessels, the gas exerts pressure, or the pressure is formed. Okay, and the magnitude of this pressure, we see the magnitude of this pressure depends on kinetic energy of the molecules and also on the number of molecules, If the kinetic energy of molecules is large, then the magnitude of pressure is also large, because with high speed the molecules will collide on the walls of the vessel. That's why the magnitude of pressure is increases, and if the number of molecules are also large, they strike more than the low number of molecules, hence again the magnitude of pressure is large. Okay, Let's move further. We'll see the sixth assumption, sixth postulate. The average kinetic energy of all the molecules is proportional to the absolute temperature, This is important. The average kinetic energy possessed by all the molecules is proportional to absolute temperature. If we change the temperature, there is change in the kinetic energy of the gas molecules. The seventh postulate is all molecules of any one gas have same mass and size. Okay, but simple, they differ in these from gas to gas. Okay, so all the molecules of any one gas have the same size and mass, but they differ from gas to gas. Okay, and what is the eighth postulate? Eighth postulate is the effect of gravity on molecules, on the molecules is negligible, since they have low mass. Since the molecules are lightweight, the effect of gravity on molecules is negligible in comparison with the effect of continued collisions between them. Okay, and the ninth postulates and last one is the laws of classical mechanics. We know the classical mechanics, that is Newton's law, are applicable to the motion of gaseous molecules. Okay, so these are the total 9 postulates. Okay, if you read again and again, you will understand the meaning of this, and these assumptions are important from the examination point of view. So study them well and prepare for the examination. Okay, in this lecture we are going to derive the kinetic gas equation. Okay, so what is the point? Derivation of kinetic gas equation. Okay, so clearly watch the concept so you can easily understand. On the basis of postulates of kinetic molecular theory of gases, we can develop an important equation named as kinetic gas equation. So this equation is based or deduced by using the assumptions that we have seen in earlier lecture. And this kinetic gas equation expresses PV of gas in terms of number of molecules. Okay, so the kinetic gas equation, it expresses the PV of gas in terms of number of molecules. Okay, and molecular mass and molecular velocity. Okay, so this is the statement of the kinetic gas equation. Okay, so how to derive this? Let's move further. So let us consider a certain mass. Let us consider a certain mass of gas enclosed in cubic box. Okay, as shown here. Okay, so this is the cubic box, and in this cubic box a certain mass of gas is enclosed at fixed temperature, and this box is kept at fixed temperature. Now suppose that length of each side of box is L centimeter. Now, so what is first? Length of each side of box is equal to L centimeter. What is the second? Total number of gas molecules is equal to small n. Third, mass of one molecule, mass of one or single molecule is equal to small m. Okay, and the last one is velocity of a molecule. Velocity of a molecule is equal to v, small v. Okay, so after considering this, the kinetic equation may be derived in following steps. So there are different steps involved in the derivation. Okay, so one by one we'll see the steps. Number one step, resolution of velocity v of a single molecule along x, y and z axis. Resolution of velocity v of a single molecule along x, y, z axis. Okay, according to the kinetic theory of gases, a molecule of gas can move with velocity v in any direction. We know this. Okay, so molecule can move anywhere in the available space. Okay, then we know the velocity is vector quantity. Okay, and this can be resolved in the components Vx along x-axis, Vy along y-axis, and Vz along z-axis. These components are related to velocity v by the following expression, that is v square is equal to vx square plus vy square plus vz square. Okay, so this is the velocity v, okay, of three components. Now we can consider a motion of single molecule moving with the component velocities independently in each direction, okay, along these three axes. So what is the second step? Okay, let's move further. The second step is the number of collision collisions per second on phase A due to one molecule. We are considering only one molecule. Okay, consider a molecule moving along x-axis. Okay, so this is the molecule moving along x-axis between opposite faces A and B. This is face A, this is face B, and this is the molecule. It is moving between opposite faces A and B as shown in this figure along x-axis. Okay, the molecule is moving along the x-axis towards the face A and towards the face B. Okay, and the length is L centimeter. Length of each side is L centimeter of the box. Now the molecule will strike the face A. A molecule which will strike the face A on the right side with velocity Vx. And after striking it will rebounce with velocity minus 6. So rebounds with velocity minus Vx. Okay, so if this is the molecule, this moves here, strike the face A here with velocity Vx, and after striking it will rebound towards the face B with velocity minus Vx. Okay, so to hit the same face again, to hit the same face means once the molecule will come here and it will go back to B and again it will come to A. Okay, so to hit the same face again, the molecule must travel L centimeter length to collide with the opposite face B. To collide with opposite phase B. Okay, so from here, from phase A to collide with phase B, L centimeter distance is required to travel. Okay, and then again L centimeter to return to phase A. That means this molecule strike on this, it has to go to B by traveling the L centimeter, and to strike again the same phase, the molecule has to come back by traveling again another L centimeter distance to strike for the same phase. Okay, so therefore the time between two collisions, the time between two collisions of phase AV is equal to 2L, 2 times length divided by Vx. Seconds. This is seconds. And number of collisions per second on phase is equal to A is equal to Vx divided by 2L. Okay, so I hope all of you have understood this. So keep this image in your mind, this box and these molecules with velocities and length of the box. Okay, so let's move further. Then the third step is the total change of momentum. The total change of momentum on all faces of the box due to one molecule. Only. Okay, we have seen for one molecule only. So we have to see now the total change of momentum on all faces of the box due to one molecule only. So each impact of molecule on phase A, each impact causes a change of momentum, that is mass into velocity. Like this, the momentum before the impact, first one is the momentum before the impact is equal to mvx. Okay, the momentum after the impact is equal to m minus vx. Therefore change in momentum is equal to mvx minus mvx is equal to 2mvx. Okay, but the number of collisions number of collisions per second on phase A due to one molecule as seen earlier is equal to Vx divided by 2L. Okay, therefore total change of momentum per second on phase A caused by only one molecule is equal to 2 mVx into Vx divided by 2L, which is equal to, the 2 and 2 will cancel, m Vx square divided by L. So this is the total change of momentum per second on phase A caused by only one molecule. Now let me finish this, or I will erase this. Okay, then the change of momentum on both the opposite faces, A and B along x-axis will be double. Okay, that is 2mVx square divided by L on both the faces. Similarly, change of momentum along y-axis and z-axis will be on y-axis 2mVy square upon L, and along the z-axis 2mVz square divided by L. Okay, respectively. Hence, overall change of momentum. Let me clear this. Then overall change of momentum per second on all faces of the box, that is along the all three axes xyz, is equal to sum of this all 2m Vx square divided by L plus 2m Vy square divided by L plus 2m Vz square divided by L is equal to 2m common, L common, which come out of the bracket, Vx square plus Vy square plus Vz square. Okay, and which is equal to 2m V square divided by L. Why? Because V square is equal to Vx square plus Vy square plus Vz square, as we have seen earlier. Okay, so This is the total overall change of momentum per second on all faces of box. Okay, then we will move towards next point, next step. That is fourth. What is fourth step? Total change of momentum. Total change of momentum due to impacts of all the molecules on all the faces of the box. We have seen for one molecule, now we are seeing for all the molecules on all the faces, the total change of momentum. Okay, suppose there are n molecules. In the box, each of which is moving with a different velocity, that is v1, v2, v3, etc. Then total change of momentum due to impacts of all molecules on all faces of the box, it is equal to 2m divided by L into bracket v1 square plus v2 square plus v3 square plus so on. That is velocities of all the molecules. Multiplying and dividing by n on this equation, will get the total change of momentum. The total change of momentum is equal to 2mn divided by L into bracket v1 square plus v2 square plus v3 square plus so on divided by n, so which is equal to 2mn u square divided by L. So this is total change of momentum of all the molecules and on all the faces of the box. Okay, where u square is mean square velocity. Okay, so this is important equation, total momentum. Keep this in mind. Then the fifth step, calculation of pressure. From change of momentum and final kinetic gas equation. Okay, since force is nothing but the change in momentum per second, we know force is equal to, or it is the change in momentum per second. So we can write force is equal to 2mn u square divided by L, but pressure is equal to total force divided by total area. Total area, that is P is equal to 2m nu square divided by L. This is the total force into 1 upon 6L square, that is the total area, which is equal to 2 3 are 6, so 1 divided by 3 mn u square divided by L cube. Okay, and again the L cube is volume of cube. L cube is volume of cube, that is phi, and hence the equation becomes P is equal to 1 upon 3 mn u square divided by phi. Okay, very simple. So if we transform this V to this side, we will get PV is equal to 1 by 3 mn u square. So this is fundamental equation. Fundamental equation of kinetic molecular theory of gases, and this is known as kinetic gas equation. Kinetic gas equation. So keep this equation in your mind from the examination point of view. Okay. Then, though the equation is derived from for a cubical vessel, it is equally valid for a vessel of any shape. So we have seen this for cube, but this can hold for any kind of shape. The available volume in the vessel could be considered as made up of a large number of impersonally small cubes for which the equation holds. Okay, now we'll see significance of the term u, that is mean square velocity. Significance of term u, as we have seen in step 4, u square is the mean of squares. Mean of squares of the individual velocities for all n molecules of gas, but u is equal to under square root u square. Therefore u is called root mean square velocity. Okay, that is RMS velocity. Now we have to see the kinetic equation. Kinetic equation in terms of kinetic energy. Kinetic energy. We'll see this. If n is the number of molecules in a given mass of gas, then we have kinetic gas equation as PV is equal to 1 by 3 mn u square. Okay, so we transform this equation into this form: 1 upon 2 by 3, that is multiplying this equation by multiplying and dividing this equation by 2 divided by 3n into 1 upon 2 mu square. Okay, so which is equal to 2 by 3n into E is equal to 2 by 3 E, and where E is the average kinetic energy, of a single molecule, and E is total kinetic energy of all the molecules. The expression, this this equation is called as the kinetic gas equation in terms of kinetic energy. Comparing this equation with the general equation, PV is equal to nRT, PV is equal to nRT. Comparing this and this equation, we can write 2 by 3 E is equal to nRT. For one molecule, the kinetic energy of n molecule is E is equal to 3 by 2 RT. Okay, since the number of gas molecules in 1 mole of gas is N0, that is Avogadro number, we can write the E is equal to E divided by N0, that is Avogadro's number, which is equal to 3 by 2 RT divided by N0. This is for 1 mole of gas. Substituting the value of RT N0 in the equation, the average kinetic energy can be calculated. Okay, so there are 5 steps involved in the derivation of this kinetic gas equation. I have explained each step very slowly, so watch this again and again to understand all the concepts. So thank you for watching this.